Can y'all hear me?
Yes.
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 All right, cool. Sorry about that. Zoom decided to update itself and then it wasn't working. Okay, so let's see. All right. Let me see here. Looks like all of y'all are doing well on turning in your quizzes and exams. Bianca Williams, are you out there? I didn't receive your quiz number 2. So hopefully you can get that submitted soon. So out here in Canvas land, under files, quiz and exam solutions, here's the solutions to yesterday's quiz and exam. So if you happen to not get it done for any reason, you could still turn it in, but you're going to get half credit because the solutions are already available here. What that does mean is that you shouldn't have any zeros this semester for anything, because even if you missed it, the solutions are already right here online. You can easily just copy them down and submit them and at least get a 50. Okay. Okay, hold on. My dog is wigging out. Dexter. Get out, dude. Oh, your doggy bowl is in the way. That's your fault, dude. Come on. Okay. No, I can't play right now. You go play. He stuck his doggy bowl right in front of the doggy door and then he couldn't get in. Started tripping. So we're going to go over the exam 2 first from last class. Basically what we're going to do in each class. Beginning of the class, I'll go over yesterday's exam. So for number 1 here, we need a common denominator. So what's the smallest number that 2 divides into, 3 divides into, and 4 divides into? Okay, it's going to be 12. Okay. Sorry about that. Let me put this on silent. Okay, because 2, 3, and 4 all divide into 12. So to turn this 1/2, to turn this 2 into a 12, we need to multiply it by a 6. We can't just multiply the bottom. We'd have to also multiply the top. You see, this is the number 1. So we're not changing this value. We're just changing the representation. So to turn this 3 into a 12, we need to multiply it by a 4. We have to multiply both the top and the bottom again. So we don't change this, the value of 1/3. We're just changing its representation to 12ths. And then our 1/4 here, to turn that 4 into a 12, we'd have to multiply it by a 3. So now this is the number 1, the number 1, the number 1. So we're not changing any of these values. We're just changing the representation. So right here, we got a 6 times a 1 over a 6 times a 2. We got a 4 times a 1 over a 3 times a 4. And a 3 times a 1 over 4 times a 3. So now we're looking at all 12ths. Since it's all 12ths, we could just add across. 6 plus 4 plus 3, 12ths. So this would be 13 12ths, also known as 1 and 1/12. However you want to write it is fine. All right, number 2. All right, it's the same thing. We need a common denominator. We're going to go for 12ths. We already know from up here, it's basically exactly the same thing, except we have a minus sign, right? So watch this. We could just go. It's exactly the same, except we have a minus. So this is going to be a minus. This is going to be a minus, which makes this a minus. Okay, it's exactly the same problem. So you got a 6 minus 4 is 2 plus 3 is 5/12. Y'all follow that? All right, if you get the first one, you should be able to get the second one. Okay. Any questions? All right, now that we've got exam done, we're going to have the quiz for today. This is going to be quiz number 3. Since we haven't covered any material yet, I'm going to give you some more fractions here. I want y'all to add 1 over A plus 2 over B plus 3 over C. And this one, let me change that to a minus. Okie dokie. So y'all take 10 minutes. You could work together. I'll put you into breakout rooms. So I'll work this for y'all at 10:21. So here's your breakout rooms. And ready, go. All right, class, welcome back. So now we're going to work the quiz. So there's no reason all of y'all should not get hundreds on all the quizzes, because even if you miss the Zoom today, the notes are going to be online right after class. So you can always look at the solutions in the lecture notes after class. You only need to get your quiz uploaded by midnight tonight. So I want to see hundreds on everybody's quizzes all the time. All right, so for number 1, we need a common denominator. And this might be odd because we have A's and B's and C's, but remember, they're just numbers, right? We just don't know what they are, but it's a number. Our common denominator here is going to be A times B times C, right? Whatever A is, whatever B is and whatever C is, if you multiply them all together, that would be our common denominator. So this one here doesn't have a B or a C. These have B's and C's. This one doesn't. So what this one needs is a B and a C on the bottom. But whatever you do to the bottom, you have to do the top. This is the number 1. So we're not changing this value. Whatever that value is, we don't change it by multiplying by the number 1. We've just changed its representation. So the second one, the 2 over B, right? The others have an A and a C. So it's missing an A and a C. So we're going to give it an A and a C. Again, this is another smart one. And now this 3 over C, it doesn't have an A and a B. So if we give it an A and a B on the bottom, we have to do it to the top. Now they all have A, B, C, right? So this one here, we have a BC times 1, which is just BC, over an ABC. And here we have 2AC. And yeah, it's BAC, but that's the same thing as ABC. It's custom to write the letters in alphabetical order. It's just prettier that way. And then we have a 3AB over ABC again. So we put all these together, we have a BC plus 2AC plus 3AB all over ABC. And we can't combine these. Remember, these are not like terms, right? This one has a B in it, and this one doesn't. You see, they're not the same. They'd have to be exactly the same letters for us to be able to actually add them together and combine them. So that's the best we can do as far as adding these together. Any questions about this? right? I know y'all had this in elementary algebra, but you know, it bears repeating. So this guy, it's going to be exactly the same as this one up here, except there's going to be that minus sign. We'll go ahead and work through it. So the first one, it doesn't have a B or a C like this one does. So we're going to give it a B and a C. Now it has an A, B, C on the bottom. Our 2 over B here, the B, we need an A and a C. So we get an A, B, C on the bottom. And our 3 over C, it doesn't have the A, B, so we need to give it an A and a B. So 1 times BC over an ABC minus 2AC over an ABC plus 3AB over ABC. So we got our common denominator. We could just add the top across. And boom, we could do our touchdown dance. Problem solved. Any questions? Okay, so
So not every problem comes down to where it makes sense. Like I get it, when you explain it, it makes sense, but like not every answer is gonna look like it makes sense.
right, it's not always a pretty answer, right? You know, it's just a lot of practice, getting it to where you could go through all this without making a mistake. You know, a lot of times we kind of get it, but it's just a matter of practicing to where we get that confidence to where we could work it through. And even if the answer looks ugly, we'd be confident that it's correct. So practice, lots of practice. You know, I play Fortnite and these 5-year-old kids kick my ass all the time. And on that video game, you know, you run around and kill people, shoot at people. It's multiplayer. And it's like people think math is hard. You know, it's like I've been doing math for 20 years. You know, I think I'm pretty good at it. You know, it's like math is something that if you practice, you eventually get it. You know, something like Fortnite, no matter how good, you know, how much you practice, there's still a 5-year-old out there that could whip your ass, you know? So, you know, yeah, math is hard, but it's not nearly as hard as a lot of the things that we do every day. You know, it's just that we do it every day that we're so good at it.
Gotcha.
All right, is there a cheat sheet? Well, basically it's the rules of adding fractions. You have to get a common denominator. That's your cheat sheet, is the steps. The steps is find your common denominator. In this case, it's ABC. So the next step is make sure that each fraction has the same thing on the bottom. Once you do that, you can add them across, add the top across. So that's basically your cheat sheet. So fractions give a lot of people trouble, right? But it's really just 2 steps. Get your common denominator and then add the top across. Okay. Oh, there we go. Effortlessmath.com, TSI math cheat sheet. All right. With the goal, mathematicians notoriously suffer from CRS. We can't remember shit. We basically figure out everything from basic principles. I can't remember my multiplication table, no matter how hard I try. All right. So math is not about memorizing, you know, but at first you memorize things so that you can get it down. But eventually, once the understanding clicks, you go, oh, and suddenly 10,000 things that you used to memorize becomes one simple logical step. So like pre-calculus, it's the whole class is the Pythagorean theorem. And this is one, a squared plus b squared equals c squared. That's all of trigonometry. It's just all the things you can do with that one equation. And there's 10 billion things you can do with it. And so you start off by memorizing a whole lot of rules and stuff. But by the end of the class, you start to see the connections. And it's like, oh, I don't need to memorize all this stuff. I could figure it out with 1 or 2 steps from the Pythagorean theorem. Yeah, exactly. All right, so let's look at our book here. Here's our packet. I hope I have the up-to-date one. Does anybody have a copy of this that's newer than this for any reason? I think
I think that's the one I got.
this is the one I used last semester. It's the one I put on the website. I don't know if they updated it since last semester though, but it should
I
have.
don't think so, because when I went down to SAC, that was the only one that they had
Okay,
to give us. So I assume it's the correct one.
all right, cool. So yeah, remember with math, it doesn't matter where you're at, whether you're in Cal 10 or you're in, Math 1, it's the same difficulty level. No matter how much math you know, you're at the edge of your own knowledge because there's an infinite amount of mathematics. Not all of it has been discovered yet. So even Einstein, math was hard for him. He was working at a different level, but you always feel like this is really hard and I'm not sure if I can understand this, basically the key to learning math is simply believing in yourself and overcoming insecurities. That's what it's all about, is believing that you could figure out this one little logical thing. And it seems impossible. It seems impossible. And then when it finally clicks, then suddenly it's obvious. And it's so obvious you can't figure out why you couldn't have figured it out in the first place. And you never know. You keep working with it, and you might be 10 seconds away from it clicking, but you still feel like you're looking at it for the first time. Okay, so just don't give up and know that, it's all about practice and effort, and it helps to go to the tutoring lab. Sometimes, I remember spending, 10 hours looking at something and not getting it, where, if I'd had the right tutorial or an animation instead of just symbols to look at, I would have been able to figure it out a lot more quickly. So you have to do the work, but at the same time, it helps to work with others. Even if you think you understand it, explaining it to somebody else that doesn't understand it, they might understand it in a different way than you do. So helping others really helps you learn it more deeply. You can see it from a different point of view. So let's start off with some simple stuff here. Let me figure out how there's my button. So percents, I'm going to hound you with percents this whole semester because it's one thing that shows up in your life that you will use all the time. Percents and proportions. Okay. This is something you want to get, integrated into your neural network, right? Remember, when you learn something, it's just like going to the gym, right? When you go to the gym, you can't go to the gym for 24 hours straight and come out buff. You have to do it a little every day because it's actual muscle fibers growing. The same thing goes with learning. Every single thought you have, there's a little neural connection that's being made. And so as you study math a little every day, what you're doing is you're rewiring your brain literally, and that simply takes time. All right. So that's why you have to do it every day, at least a little bit. Okay. But it's hard to, you can't do it all day long. You'll burn out, just like you can't sit there in the gym and work out all day long. Your body just can't sustain that, right? For your neural network to actually rewire, that requires proteins and ions and anions and little electrical impulses that are, actually building the physical network in your brain. So it's an actual physical process that's going on in your head. Let's look at, let's see, I hope I hit the button here. Okay, I did. All right, percent or proportion. Write a ratio or fraction that represents the shaded portion in each of the following figures. Figure out which ones are equivalent. So this one right here, number one, we got 1, 2, 3, 4, 5, 6, 7, 8 total pieces, and they're all equal in size. Only one of them, 1 out of 8, is shaded, right? Over here we have 1, 2, 3, 4, 5, 6, 7, 8. So we still have 8 total, but 3 out of the 8 are shaded. Now over here, we got 1, 2, 3, 4, 5, 6. We still got 8 slices, but 6 out of the 8. All right, and are shaded. And this is actually a ratio we can simplify, right? 6 is 2 times 3, and 8 is 2 times 2 times 2. So notice you can drop this 2 out of the top and the bottom, and we're left with 3/4. So 6/8 is the same as 3/4, right? All right, and we'll get into this stuff more later. Your algebra, arithmetic, fundamental theorem of arithmetic. You can always write a number as a product of primes. So prime decomposition. We'll get into that later. Some basic fun stuff. So let's look at these blue ones down here. Here we got 1, 2, 3, 4, 5, 6. So we got 2 out of 6, which we could simplify. 6 is 2 times 3. And we can write 2 as 2 times 1, right? So the 2's go away, and we're left with 1/3. So 2 out of 6 is the same as 1 out of 3. Now for number 5, we got 1, 2, 3. So 2 out of 3 are shaded. So it doesn't look like any of these are equivalent. All right, numbers 1 through 5 here. I don't think any of those are equivalent. So let's look at the next page here. We got 2 more.
But are we working the percentage on that too?
Right now, they just want us to write the ratio. All right, so we'll build up to the percentages. All right. Of course, I mean, 3 out of 4 is what, 75%, right? 3 out of 4 as a decimal is 0.75, which is 75 out of 100. That's what they mean by percent, per century, per 100. So 75 per century. So 75 over 100, this is 75%. That's all that percent means. Percent is per century. That's all that symbol means. Okay, it's the division symbol over 100%. That's why they call them dollars and cents. The cents, there's 100 cents in a dollar. Just the other day, I saw a place called Alphabet for little kids. And I realized that, we call them the ABCs. Well, in Greek, it's alpha, beta, gamma. So the word alphabet, all that really is AB in Greek. And I thought, man, that's lazy. At least we call them the ABCs. They just call them ABs. But then I thought, well, we call our letters A, B. It's like, what sound does it make? A? Oh, let's call it A. At least they had cool names for their letters, like alpha, beta, gamma. That's so much cooler than us. We just like A, B. Oh, it's D. It's all it is the sound. It's like, couldn't we have cool names for our letters, All right, so number 6. So we got 1, 2, 3, 4. So we have 3 out of 4. All right, if we wanted to convert this, it's the same. It's 3 out of 4 as a decimal is 0.75 or 75 out of 100, right? Which would be 75%. If you don't know this, 3/4, all we have to do is rewrite this fraction where there's 100 on the bottom. So what I could do is multiply this by 25 over 25 to make 100 on the bottom. See, 3 times 25 is 75, and then I have 100. So this is a 75, and this right here is percent. All right, so that's one way to do it. This way up here would be like using a calculator. Plug it in, get the decimal. Dividing by 100 moves decimal to the right twice. But here's another way of doing it without a calculator. Oh, by the way, with calculators, I'm going to do the whole class with the basic calculator that's on my iPhone. Right? So you don't have to have some big expensive calculator, you know? We have phones, you know, and these phones are computers that are more powerful than any calculator we're gonna buy, you know? And that's something we're gonna have with us, you know? All right, over here, we got a 1, 2, 3, 4, 5, 6. Right? How are we gonna do this? Here, let's see. How do I want to explain this? Here we have 3 out of 3, right? And over here, we really want to do it 1, 2, 3. Okay, we have 2 out of 3. All right, so if we want to add these together, all right, 3 out of 3 is 1, and then 1 2/3. All right, so let's see, how can I explain this? Because 1 2/3 is not the same thing as 5 out of 6, right? 5 out of 6 is less than 1. So what we're really looking at is 1 whole one and 2/3 of another one. Let's see if we added these together, 3/3 and 2/3, that's 3 plus 2/3. This would be 5/3, right? 5/3 is the same as 1 2/3. But notice what I did at first. I was like 1, 2, 3, 4, 5, 6. I had to said 5/6, right? 3, 4. That is wrong. All right. This is not 5/6. 5/6 is less than 1. We have 1 whole one and then 2/3 of another one. Okay. That's why we have to number them with the start over. Okay, because this is 1 whole one. Okay, so this is the way we want to do it down here. All right, let's see here. Page 6. Discuss and answer the following. Draw a picture representing 1/4. All right. There's 1 out of 4, right? Draw a picture representing 4/1. Okay. All right. Let's see, I could do like this. All right, here's 1, here's 1, here's 1, here's 1, right? I could write this as 4 out of 4, 4 out of 4, 4 out of 4, 4 out of 4 if I wanted, right? 4/1 is 4. We need 4 whole, you know, squares or whatever. Whereas this one is 1/4. This one over here is 4 total, right? So no, they're not equivalent. 1/4 is not the same thing as 4, right? Right, 25 cents is not the same thing as $4. All right, when is it necessary to write 1 in a ratio? All right, well, the number 1 can be written a million different ways. The number 1 is 2/2. It's 3/3. It's 100/100. It's $1/100, right? It's 1 mile over 5,280 feet, right? As long as the top and the bottom are equal in value, you have the number 1. All right, so we're going to use the number 1 in a multitude of different ways. And the reason why we want to do that, we use smart ones, right? We did it up there in our quiz in order to get a common denominator. So for common denominators, because when you multiply by the number 1, you don't change the value. But if you use a smart one, you can change the representation. For instance, if I want to do unit conversion, Unit conversion. All right, if I got 52 cents, if I want to change this into dollars, I will multiply it by the number 1. But I will use a smart version of it. I got cents. I'll get rid of the cents. I want dollars. I know that $1 is the same as 100 cents. So the cents cancel out and I'm left with dollars. So I got 52 out of $100 or 0.52 dollars. So we use, these are two ways that we use number 1 written in a ratio. They're called smart ones. Okay. That's just 2 examples. So yeah, the number 1 is really, really powerful. Again, we didn't change the value, we changed its representation. You can do the same thing with 0, because when you add 0, it doesn't change the value. Well, you can write 0 an infinite number of ways. So that's useful too. So why? Oh, they put the 4/1, right? Why did they put the 4/1? They did it to try to confuse you. Up here, 4/1 is just 4, right? But they wrote it over 1 just to mess with you. They wanted it to make it look like this, so they could try to mess with your mind. But yeah, anything can be written, anything at all. X is X over 1. You can always write it like that. Say if you're trying to compare it to something else that's over 1. All right. Where was it? Okay. Page 7 here. Identify the part from the whole, then form the associated fraction. All right, I'm going to try to decipher what they mean by that. All right, he tipped $8 on a $22.58 ticket. So the whole, I'm guessing here, is the $22.58 plus the $8, right? So that's the whole amount that Tony paid. That would be what, $30.58, right? That would be the whole. And the part, I guess, is the tip. So $8 out of 30.58, right? So we're looking at the percentage of the whole bill that was the tip, something like that. I'm just guessing at what they mean by the whole. Okay, let me get my calculator out here. Let's think about this a little differently. I'm thinking maybe let's not look at it like that. If you tip $8 on 22.58, maybe what they're looking at here is what percentage did you tip, right? For a 22.58, so they're thinking as this as the whole, right? You tipped $8 on 22.58. If I plug this into my calculator here, 8 divided by 22.58, this is 0.354, keeps going, right? So what I'm going to do is I'm going to round this off. So when you round, we have a different symbol for equals. It's squiggly equals. All right, that means approximately equal to. So we use this equal when it's exact. We use this equal when we've approximated. So this would be 35.4%. Okay. And why is that? Again, we're going to get into this percent more in detail. I'm kind of jumping ahead here. All right. This is 35.4 over 100. Right. When you divide by 100, you're moving the decimal twice. So that's why it's 35.4%. This question right here, all they wanted you to do is write that down. Okay. Okay. So this is extra stuff, this percentage stuff. All right, so let's look at this one. Maybe it'll be more clear as to what they mean by part and whole. So an 82 game regular season, the Spurs won 58 games. So they won 58 out of 82. So this is the part, here's the whole. All right, so this one is more clear as to what they mean by part and whole. All right. So Northwest Vista has 15,435 students, 4,630 of them will transfer to UTSA. So 4,630 out of 15,435. All right, is how many will transfer. So we could actually get a percentage here if we wanted to. They don't ask us to do that. They're only asking us to do this, but I'm going to go ahead and do the percentage anyways. So if I plug this into my calculator. All right, I'm getting 0.2, approximately, let's put 0.3. All right, so as a decimal, I could rewrite this as 30 out of 100, right? I'm just moving the decimal twice. So this would be 30%. So 30% is going to UTSA. Let's look at these. All right, Sam has caught 212 out of 802 Pokemon. We plug this into our calculator. I'm getting approximately 0.26. So this is 26 out of 100 or 26%, right? Remember, this means this. All right, my paycheck would have been 950, but 170 was taken out for income tax. So 170 out of 950. So let's see what kind of taxes he's paying. What percentage? 170 divided by 950 is approximately 0.18. So that's 18 out of 100 or 18%. That's a lot of taxes, huh? All right, let's check out Heidi here. Okay, Heidi is on a 5 3/4 hour car trip. She has driven 2.5 hours so far. So she's driven 2.5 out of 5 3/4. All right, or 2.5 out of 5.75. If we plug this into our calculator, 2.5 divided by 5.75, I'm getting approximately 0.43, which would be 43 out of 100 or 43%. All right, we're going to take a 10-minute break here. So grab you some breakfast or something. I'm trying not to fall out here, soaked in sweat. We'll come back and I'll see how much further I can go. We might end class a little early, but we'll typically have like a 10-minute break in the middle of class. So we'll be back. Break. Return at 11:05. Okay. Get you some exercise in or whatever. So we'll start back in 10 minutes. Okay, class, we are back. See how much longer I can persist here. I was melting in my chair a while ago. All right, here we go. Number 8. Prepping for percent and proportion. All right, identify how the following numbers and variables are held together by addition, subtraction, multiplication, or division. So here, X is a number, 5 is a number, are held together by subtraction. Here we have multiplication. Here we have division. Here we have addition. Here the dot means multiplication. See, we don't use this in for multiplication very often in mathematics until you get to higher level math. See, when we're little kids, they always use this. And then you get into algebra and people mistake that for the letter X. And that's the reason why so many people have so much difficulty with algebra, is because they use this for multiplication and then they use the same thing for X, right? And that's just messed up, right? Typically you use a dot or you just write them right next to one another. That's multiplication. Okay. When you get into higher level math, there's a lot of different kinds of multiplication. There's the regular multiplication, the scalar product, the dot product, the cross product, right? Multiplication is also known as the product. So in higher level math, where you end up multiplying not just numbers, but you have like data structures. You might have an array of numbers, like here's a number, right? This would be called a matrix. So it's a collection of 9 numbers. Then you might cross multiply it with another matrix, or you might dot product, or you might scalar product. So that's just one example of how you can have different kinds of multiplication, because we have more than just numbers in math. You have collections of numbers and other relationships. Most of math, I mean, the numbers, this is just arithmetic. When you have numbers, when you get into higher level math, the only numbers in the textbook are the page numbers. Everything else is symbols, because what you're really looking at is the logical relationships between things. So that's why, like, being a lawyer, you really need to be a top-notch mathematician, because it's one and the same thing. To be able to prove something, given facts X, Y, and Z, prove, outcomes A, B, and C. And it's all the same thing, right? Math is not just about the numbers. The numbers, that's just arithmetic, right? In other countries, they call it maths with an S, right? Here we just call it math, but it really is maths. There's lots of different kinds of math. You have algebra, you have trigonometry, you have calculus, you have linear algebra, you have category theory, you have number theory. And every single different sub-subject of math is completely different. And, like geometry and algebra historically came out of 2 completely different regions of the world, 2 totally different civilizations, 2 completely different approaches to symbolic logic. All right. So if you have trouble with numbers, that doesn't mean you can't be really good at algebra. And if you're not very good at algebra, that doesn't mean that you might not be great at calculus. Okay. We'll finish this. I'm going to show you something cool. So here we got a -7 plus an X. We're adding. Here we're dividing. Here we're multiplying. Here we have 2/5 times an X. So we're multiplying.
Sorry, Zoe was asked a question about the matrix.
Oh, yeah. What are they used for in the real world? Let's say video game programming, right? You see, what do we multiply? Instead of just a number times a number, right? That's great if, like, you're trying to say, let's see, distance is velocity times time. So if you take how fast you're moving times the time you've been traveling, you get the distance, right? Well, what if you want to know about in 3-dimensional space, right? So your location in 3-dimensional space is an X, a Y, and a Z. It's not just X, right? X could tell you how far in one direction, but you need to know how far left and right, how far up and down, and how far right and left. So this would be a column vector, right? So if you're dealing with like rotation in 3D space, you're gonna have a three-dimensional matrix, and then you're going to multiply it by a transformation matrix. All right, and that's going to tell you the orientation of an object in three-dimensional space. So the matrices could be transformations. So let's say, what if you're working, you got something, imagine it in 3D, but this is 2D. You got some kind of object. It's kind of weird, right? Well, if I can hit this with a matrix and I could turn this squiggly line into a straight line and then do whatever operations I wanted to do, you know, because of dealing with a straight line is easier than dealing with a squiggly line. So you transform it to where everything's pretty, do all your work, and then you do the inverse of this and transfer it back. That's one example. You'll see at the end of this class, one thing that y'all can actually do using matrices is solving equations. So if you have an equation, y'all know how to solve for x, right? If I have x plus 7 equals what, you could solve for x, right? Well, what if I have x plus y equals 3? Well, now I have two variables, right? So the solutions to that, there'd be an infinite number of them, which we'll see at the very end of class. Okay, but I'd have to have two separate equations to get, like if I had this x plus 2y equals 1. I have two equations with two unknowns, and I can use this to solve for the x and the y. There'd be one x and one y. Basically, this is a line, and this is another line. Where they intersect is the solution to this set of equations. So if I have an x plus 2y plus 3z equals 4, and I have a 2x minus y plus 4z equals 5, and I have a 3x plus 3y plus 3z equals 3. All right, here I have three equations, and there's three unknown variables. Well, if you put them in order from x, y, and z, whenever you're trying to solve these, instead of doing the standard substituting and stuff like that, what we do is we just get rid of the x, the y, and the z. If you put them in order, the x column, y column, z column, we could rewrite this as just, this is a 1 here. We'd have a 1, 2, 3. And then this column would be a 2, a -1, and a 3. This column would be a 3, 4, 3. And then this column would be a 4, 5, 3. All right. So that would be a matrix. We just don't even bother writing the x's and the y's and the z's. Okay. And then you can manipulate this matrix to where you end up with 1, 0, 0, 0, 1, 0, 0, 0, 1. And whatever the numbers you get over here, that's your x, this is your y, and this is your z. That would be your actual solution. That would be the values for x, y, and z that would satisfy all three of these equations. There's only one set. There's only one x and one y and one z that satisfies all three of these. Okay. So each one of these would be like a line in three-dimensional space. And if they all happen to intersect in a single point, this would be that coordinate of that point. So that's how they introduce matrices. But everything like video game programming, it's called linear algebra, the manipulation of matrices and such. Okay, like general relativity, you use tensors because space-time is 4-dimensional. So instead of just an x, y, z, you'd have an x, a y, a z, and a t for time. And then space is curved, right? If you have mass, like gravity is the curvature of space-time. So you'd have to have what they use is tensors and Christoffel symbols to have the twisting and the bending of space-time itself. So you use these with differential equations too. Calculus tells you how things change. So you need to have slope and stuff like that. I'll give you some more glimpses of this stuff later. Okay. I don't want to like pound your head in, but I just want to give you a glimpse of, the coolness that can come. Yeah, I struggle with matrices too.
My brain, I've never dealt with matrices.
Right, at the last day of class, we'll actually use them, and they're a lot easier than you think. All right, the basics. But I mean, you can go into it, you can write a 50-page thesis on why 1 + 1 is 2. You can make any simple concept as complicated as you like, So I'm trying to take complicated concepts and make them as simple as possible here.
Thank you. I'm gonna show Neat that because I have a son that's a freshman in high school, and the homework he does in his algebra it's. I'm like, man, I haven't been to school in 20 years, man. My math wasn't that hard in the 9th grade.
Right. All right, let's get back on track here. So now we're talking about inverses. So undoing stuff. How do you undo addition? Well, you subtract, right? So here they're adding 5 to our x. So in order to undo what's done to the x, we need to subtract 5. We'd have to do it to both sides though, right? Okay, so for this one, if you have x plus 20 equals 75, this is a mathematical sentence, right? So I'm going to show you a new symbol. This symbol. This means if and only if. It's logical equivalence. So this is a statement. If I subtract 20 from both sides, this is a new sentence. This says that these things are logically equivalent to one another. This is like saying, Yoda saying my skin is green, and this is like saying green, my skin is. It's the exact, they contain the exact same information. So this is the symbol that you use to connect sentences in math to make paragraphs. It keeps you from just having random stuff written all over the page. This is what connects them, so you can actually put together sentences to make a paragraph. Okay, so what I'm saying is this is logically equivalent to this. This thing is a combination of this and this. This is an implies thing. It's like if A, then B, that means A implies B, right? This is just going in the opposite direction. So if you get both directions at the same time, those are logical equivalents. So one is like correlation, right? A lot of people mix up correlation with causation, right? So you'd be like, all these criminals, right? They all breathe air. Well, that doesn't mean that everybody that breathes air is a criminal, right? All right. It doesn't go both ways. That's a one-way, that's one-way implication, right? But it's not an illogical equivalence. But these two statements are logically equivalent. They say the exact same thing. And in fact, what they say here, if I subtract the 20 off, I get an x, and over here, 75 minus 20 is 55. So this is equivalent to this is equivalent to this. Saying x equals 55 is exactly the same thing as saying x plus 20 equals 75. It's just a different way of stating it. This is all about x. This has x in it, right? But it's a little less direct, right? I went to the store I went, right? It's just depending on what you're emphasizing in your sentence, So you'll use this symbol a lot in here. It won't be in the packet anywhere, but it'll help y'all. Okay. That way you don't just have stuff. Like I see people, they'll do their homework. They got some stuff here and then they write some stuff over here. And then they just have random crap just kind of, it's like shotgunned onto the page, right? All right. This is how you connect statements to make a logical argument. That way it looks more like a paragraph instead of just random stuff. Okay. All right, how do you undo subtraction? Well, you use addition. So how would you solve x minus 5 equals 2? Well, we would add 5 to both sides. So we're gonna try it here. If we have an x minus 12 equals 30, this is logically equivalent to the same thing, but if we added 12 to both sides, just logically equivalent to, if I reduce those go away. 30 plus 12 is 42. Okay. So those showing all the steps. All right. This is exactly the same information as this. How do you undo multiplication? Division. So if you have 3x equals 63, they've multiplied the x by 3. So in order to undo that, we divide both sides by 3. So if we have 4x equals 88, this is logically equivalent to, we divide both sides by 4. Why? Because 4 over 4 is just 1. 1x, right? And 88 divided by 4 is what, 22? And I'm not going to write the 1 times an x. 1 times x is just x, right? Okay. Are x minus 3 and negative 3x the same thing? Hell no, they're not. Here you're subtracting 3 from a number. Here you're multiplying a number by negative 3. Okay. You could tell, right? Let x be 0. Just pick a number. Then x minus 3 would be 0 minus 3, which would be negative 3. But negative 3x would be negative 3 times 0, which is 0. Negative 3 is not the same thing as 0, right? So right there, we showed that they're not the same thing. We just picked a number, plugged it in for x, and showed they're not the same thing. Now here, we want to solve for this. All right, well, they're subtracting 3 from our x. Well, this is logically equivalent to if I added 3 to both sides of this equation, because those would cancel, and I got x equals 12 plus 3 is 15. Exactly, tautology. All right, how would we solve negative 3x equals 12? Well, we're multiplying the x by a negative 3, right? So we just divide both sides by a negative 3. Negative 3 over negative 3 is just 1. So we have x equals negative 4. 12 over 3 is 4. The minus, it doesn't matter if it's on the top or the bottom. There you have it. All right, what operation does a fraction bar stand for? Well, division, right? What operation do you use to undo division? Multiplication. So how would we solve x over 4 equals 15? We'd multiply both sides by 4. Boom. So if we have x over 5 equals 20, what we would do here is we would multiply both sides by a 5. So we get x equals 20 times 5 would be 100. Sometimes I'll cheat. I'll use my own notation. All right, I'll be like, multiply the whole thing times 5, right? And so if I multiply the left and the right, so that would be like my shortcut, you know, my own personal way of writing it, right? But this is the way, you know, the conventional way of writing things that everybody would understand, right? I mean, I think any mathematician would understand what this means. That's why I use it as a shortcut way of writing stuff. Okay. you know, if I know what you mean, then I know what you mean, you know what I mean? But you do need to know the convention as well. What if there are numbers attached to a variable by both multiplication and division? All right, well here, what I would do is I would multiply both sides by a 5 halves. You see the 2 would go away, the 5 would go away, and we're left with x. All right, so the 2 is, okay. The 2 is attached by, okay, we're multiplying, okay, the x times the 2. So we'd undo the 2 by division. Now the 5 is attached via division, so we'd undo the 5 by multiplication. So again, what did I say up here? They said 2 is attached by multiplication, so undo it by dividing. The 5 is attached by division, so undo it by multiplying. You should be able to look at this and be like, get rid of the 2s, get rid of the 5s. Now I have x by itself, and I get 50 over 2, which is a 25.
Could you go back to that one real quick?
Yeah. All right. The 2 is multiplied by the x, so I divided by 2. The x is divided by 5, so I multiplied by 5. See, it's all right here. All right, there's a 2 up here, so I put a 2 down there. There was a 5 down here, so I put a 5 up there. And I had to do the same thing to the other side. But that makes the x get left alone. All right, 5 halves times 2 fifths is just 1.
And then it was 50. So then when you times the next one is 50 over 20.
50 over 2, which would be 25.
It's
Right.
10 multiplied by 5 divided by 2.
Yeah, 10 times 5 is 50, divided by 2 is 25, right? 10 times 5 is 50, 50 over 2 is 25. Right, half of 50 is 25. Does it make sense?
This is where I'm gonna struggle. I'm confused now.
It's just a lot of arithmetic here. So let's work through it one more time. We got 2 fifths x equals 10, right? So we want the x by itself, right? So how do we get this off of its back? Well, if we multiply this thing by 5 halves, whatever we do to the left side, we have to do the same to the right side. Okay. So 2 over 2 is just 1. 5 over 5 is just 1. See, this becomes just the number 1. So we have x equals this one here. So if you want, 10 is 2 times 5. Right? 10 is 2 times 5. So you see the 2's go away. 5 times 5 is 25. It's another way of looking at it. And yeah, you're just going to need a lot of practice. By the end of the semester, you'll be good at this arithmetic stuff. Right? It's a lot of symbol manipulation.
Yeah, I think that's the only thing that's confused me. I don't know how to separate the two and when to put them together. But again, I haven't took math in 20 years, so I'm pretty sure I'll get it though.
You'll
It's my-
pick it up. It's just going to take a lot of practice. All right. You'll start seeing the patterns, and then you'll get, by the end of the semester, you'll be able to do it by reflex, you know.
One thing I did to help me separate them was I put a line on the equal sign to help me separate where the X was and where the other side of the equal sign was, the right side.
You do like that?
Yeah,
Okay,
just to help you separate them and to help you understand what you need to do from one side to the other.
okay, to keep it balanced. Yeah, whatever works, for
Yeah.
you, you know? Visual cues help. All right, what if the variable is in the denominator? Okay, well, what are we gonna do here? There's a trick, all right? I have 9 over x. 45 is the same thing as 45 over 1, okay? So here's the trick. What you could do is you can flip both sides. We don't want this on the bottom, we want it on the top. So if we flip the left-hand side and we flip the right-hand side, okay? So see what we did? We put the bottom of the fraction on the top and the top on the bottom, and we did the same thing to both sides. All right, so that's your trick. All right, so why that works, I could show you here. If you have an A over B equals C over D, okay? What I could do is I could multiply both sides by B and D. So if I did that, that goes away, this goes away. So notice I have an AD equals CB. All right. So I have AD equals BC. So now I could divide both sides by A and C. The A's go away, C's go away, and now I have DC equals B over A. So if you compare these, right, instead of C over D, I have D over C. Instead of A over B, I have B over A. So I just showed you why this trick works. If you have the X on the bottom, right, just move the bottom to the top and move the bottom to the top on both sides, okay? So that trick works. You can just swap out the bottoms and the tops. They call it the reciprocal. The reciprocal of this is this. So you just do the reciprocal of both sides. So now that the X is on the top, okay, the X is being divided by 9. So I'm going to multiply both sides by 9 because the 9 over 9 goes away. And now I have X by itself. And over here I have a 9 over 45, which I think I could simplify. Let's see. 45 is what? 9 times something, isn't it?
9 times 5.
Is that right? Yeah,
9
9 times 5. So this would be a 1/5. So X is 1/5. This is a chain equality, all right? So yeah, it's equals, 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 right? This would be called a chain equality. So notice this is connecting this equality to this equality. This only has one equal sign. This one has 3, okay? So don't let it bother you too much. You'll get used to it as the semester progresses, you know, using this symbol appropriately, right? That does not go here, right? This is regular equals, and this is logical equivalence, okay? But X equals 9 over 45, which is 9 over 9 times 45, which is equal to 1/5. So I'm saying X is equal to 1/5. All right, what if both sides are fractions? The same trick works, right? I could flip the left-hand side and I could flip the right-hand side, okay? So flip trick. So now I'm dividing by a 9. I don't want to be dividing by a 9. So I multiply by a 9. and I have to do it to both sides. So now I have that x by itself. And then I have this big mess, which I need to simplify. I'm going to do the prime decomposition. So 100 is 2 times 50. 50 is 2 times 25. 25 is 5 times 5. And then the 9 here is 3 times 3. Now 45 on the bottom is 9 times 5. 9 is 3 times 3. So all I did was take the top and rewrote them as a product of prime numbers. Remember, a prime number is a number that's only divisible by itself in 1. What that does is it allows me to simplify this fraction. So 2 times 2 is 4 times 5 is 20. You can do it any which way you want. You can simplify this fraction however you want. All right, this is just the most rigorous way to do it. All right, I rewrote 100 as 2 times 2 times 5 times 5. And I rewrote 9 as 3 times 3. And I rewrote 45 as 3 times 3 times 5. You can't break these numbers down any further than that. And the fact that you can write any number as a product of primes is called the fundamental theorem of arithmetic. So x is equal to 20. How much more do we have to go here? We got what, 20, 30 minutes? All right, we could do these. All right, number 25 here. All right, I'm going to do this with quick notation here. So they're multiplying the p times 250. So I'm going to divide both sides by 250. So P is 25 out of 250. 250 is 25 times 10, right? So I get 1/10. Over here, the n is being multiplied by a 0.45. So I'll divide both sides by 0.45. So I'm left with n equals 67.5 over 0.45, which we could plug that into a calculator and get another answer, but we don't need to do that. Right now, we're just learning how to solve for n. So that's how you would do that. So over here, let's get that out of the way. All right. We want to get this 12 over 100 off the back of x. So what we do is we multiply both sides by 100 over 12. See, the 12s cancel, 100 cancels. And so we have here x equals, let's see, 624 times 100 over 12. And we can simplify that, okay? But I'm not going to do that right now, because right now we're focusing on the how to solve for x part. So this next one. All right, the x is being multiplied by a 54 and divided by 100. Well, if it's multiplied by a 54, we need to divide by a 54. If it's divided by 100, we need to multiply by 100. So you see the 54s cancel, the 100s cancel, and we're left with x equals, I'm missing my 100, right? And multiply both sides by 100. Is 9.45 times 100 is 945 over 54. And we could simplify that too, if we wanted to, or plug it into a calculator. All right, so this one over here, I'm going to use shortcut notation. Multiply everything by 60, right? So I'm multiplying the left by 60 And I'm multiplying the right side by 60. So let's see, 60 over 20 is 3 times 7 is 21. So I have x, 21 equals x. That's the same thing as x equals 21, right? Equality goes both ways. All right, so we could put box around our answer. Over here, we'd want to multiply both sides by 100. So that goes away. So we have, let's see, 100 times 42 over 75 equals x. We can go ahead and simplify this. 100 over 75, that's the same thing as 4 over 3. All right. So 4 times 42, it's 84 times 2, it should be 168 over 3. Okay, so again, the focus here is figuring out how to get the variable by itself. So this one, the t's on the bottom, so we're going to do our trick. Flip both sides. All right. Now that we've done that trick, we want to get the t by itself. Since it's being divided by 30, we're going to multiply both sides by 30. So t is 3.4 times 30 over 5. And you can plug that into your calculator, simplify it however you want. The rest is just arithmetic. The part we did is the algebra. So we're focused on algebra right now. All right. If you're working this, I want you to also do the arithmetic. All right. So over here, we're going to do that trick again because the x is on the bottom. We're going to flip both sides. Boom. Now, because x is divided by a 14, let's get that 14 out of the bottom by multiplying both sides by 14. So we have x is 10 times 14 is 140 and then over 35. And you divide the top and the bottom by 5 and simplify that if you wanted to. All right, here we're going to do the trick again because the x is on the bottom. We can do the reciprocal of both sides. And now, because we're dividing by 19, to get rid of that 19, multiply both sides by 19. So x is 21 times 19 over 133, whatever that number is. That's what x is. With 34, the b is on the bottom, so we're going to do our flip trick here. Now the b is on the top. Now, to get rid of this 7, multiply both sides by 7. And we can rearrange this. I can write this side first. We can say b equals 7 times 16 over 14, right? X equals y is the same thing as y equals x. I could take the sides and flip them, right? Quality goes both ways.
I have a question.
Yes.
Wouldn't flipping 7 over b change its value since the 7 would be on the bottom?
Well, because I flipped both sides, it doesn't change the value.
Oh, okay.
See, if I only
Oh.
flip one side, yeah, you know, that's why you have to do to both sides. Okay, then the equality is maintained. Does that make sense?
Yes, thank you.
All right. All right, so I'm gonna cut today short here. Go ahead and give you your exam. What is this, number 3? Number 1. I want you to solve for x. Let's see. 3x equals 9. And I should do some fractions here, huh? 9 halves. 3. I'll do 3 halves x equals 9 halves there. And then I'll do 2 over x equals 3 over 4. So there's your exam. Get it in by midnight tonight. And I will see y'all tomorrow.
Okay,
Thank you.
thank
Feel
you.
better.
Bye. See you tomorrow.
Bye, everybody.
Thank you. Have a great day.
You
Thank you.